Students, good morning to all of you. Today we are coming to the new topic, gravitational field. Right? Gravitational field due to a body, any body, that can be a chalk piece, that can be a sphere, that can be a duster, any body, is the volume or space surrounding the body up to which the attractive force due to the body can be detected. Suppose a body is here, it is seen here in this figure, a body of mass m. At a distance away from this, at a distance r away from this, there is a point P. Up to P, if P is considered to be a point in the field, then if we place a mass at this point, this mass will be attracted by this big mass. This is a test mass, this is the any body of mass capital M. Now this point P is within the field of this mass. That can be a space surrounding that, a spherical volume surrounding that, inside which any point, if a test mass is placed, that test mass will be attracted by the body. Then those points are within the field, within the gravitational field of the body, right? Now one more thing is that every point inside the gravitational field of a body, there is a strength of the field. Strength of the field is called intensity of gravitational field. Any point within the gravitational field of a body, gravitational field is a spherical volume surrounding the body. Inside that spherical volume, any point, if a test mass is placed, that test mass will be attracted by the body. So within that volume, every point there is a strength, right? At a different point, the strength will be different. For example, if a body is kept somewhere in the space, a point is selected very near to the body, then the strength of the gravitational field at that point will be much more. If you take a point much away from the body, that means distance when increases, the strength of the gravitational field also increases. This is the condition. So strength of the gravitational field at different points are different. The strength of the gravitational field is also called as intensity of gravitational field. Intensity of gravitational field or gravitational field strength at a point in the gravitational field is the force acting on unit mass placed at that point. For example, you see this figure, this body is of mass m. There is a point P at a distance r from this mass. At this point P, you wish to calculate the strength of the gravitational field due to this body. What you will do? You will place a test mass m0 and will see what is the force with which this test mass is attracted toward this mass. That force is gravitational force of attraction. Sir, gravitational force of attraction. That gravitational force of attraction is given by capital F is equal to G capital M small m0 divided by r square. This is the gravitational force acting on m0. But what is the definition? Intensity of gravitational field or gravitational field strength at a point in a gravitational field is the force acting on a unit mass. Unit mass means 1 kg, 1 gram, etc. are called unit mass. Right. What is the force acting on m0 mass? That is F is equal to G capital M m0 divided by r square. This is the force acting on m0 mass by this body of mass capital M. Hence, therefore, the force acting per unit mass is given by intensity of gravitational field. It is denoted by the letter capital E is equal to F by m0. That's equal to G m0 divided by r square, the whole divided by m0. That means total force divided by total mass on which the force is acting. You will get the force acting per unit mass. That is equal to Gm by r square. Its unit is F by m0. F is Newton and m0 is kg. Newton per kg. Always remember the intensity of gravitational field at a point due to a body is whose unit is n kg raised to minus 1 is Newton per kg. Dimensions are m raised to 0, L raised to 1, T raised to minus 2. For a mass m0, m0 placed, it is not placed, placed on the surface of the earth. Suppose that a mass m0 is placed on the surface of the earth. Right? Any mass, suppose I am standing here, my mass is m0, and I am standing on the surface of the earth, and the earth's mass is me. Therefore, what is the force acting on my body by the earth? That is gravitational force of attraction acting on my body by the earth is given by F is equal to G, capital ME. ME is the mass of the earth, and M0 mass of my body divided by RA square. Why? That means the distance between my body and the center of the earth is the radius of the earth itself. That is RA square. Now, the intensity of gravitational field due to the earth on its surface is given by F by m0. What is m0 here? In this case, I am the person body whose mass is m0, means F by m0. This the whole divided by m0 when done, when you will get A is equal to G m divided by R square. But Gm by R square is equal to small g only. So, this is acceleration due to gravity. So, in the case of the earth, the gravitational intensity of gravitational field is same as equal to acceleration due to gravity. This is a very, very important point. So, on the surface of the earth, the intensity of gravitational field is numerically equal to the acceleration due to gravity at that position. So, this you can prove if the question is asked, right? Prove that on the surface of the earth, the intensity of gravitational field is equal to acceleration due to gravity. At a position h above the surface of the earth, you know that the intensity of gravitational field can be given by g dash. That means g dash is the acceleration due to gravity. When altitude increases, then acceleration gravity decreases. The value of acceleration gravity at a height h above the surface of the earth is given by g dash is equal to g me divided by r plus h the whole square. This is the intensity of gravitational field at that point at a height h above the surface of the earth. That is what it is marked here. Gravitational field strength is maximum on the surface of the earth, and it decreases when height increases. Intensity of gravitational field is maximum on the surface. Why? Because the acceleration due to gravity is maximum on the surface of the earth, and acceleration gravity is numerically same as equal to the intensity of gravitational field. Intensity of gravitational field is a vector quantity, and its direction is always towards the earth, because force is acting towards the earth. Therefore, intensity of gravitational field is also acting towards the earth. If a body is dropped from a height, then acceleration is also towards the earth. Therefore, intensity of gravitational field is acceleration due to gravity. Both are same. Right? When height increases, the acceleration due to gravity decreases, and hence from above the surface of the earth, when we go upwards, the intensity of gravitational field also decreases, and intensity of gravitational field becomes zero at infinity. This is the point. So, it is also graphically also it is at infinity the intensity of gravitational field is zero. Where is it maximum? On the surface of the earth. When we go away from the surface of the earth, intensity of gravitational field is maximum on the surface of the earth. Surface of the earth means the distance of the earth from the surface is equal to r. That means at r, from the center of the earth, when we start a journey towards the surface of the earth, the intensity of gravitational field goes on increasing, and it becomes maximum on the surface of the earth. So, from the center to the surface of the earth, the intensity of gravitational field is proportional to the distance. Proportional to the distance means it is going on increasing proportional to the distance, right? And now when we go away from the surface of, it is inversely proportional to distance. Am I correct? So this is E is directly proportional to R. This is E is inversely proportional. E proportional to 1 by R we must write. E proportional to R you will write. This is the condition. That means at the center of the earth, why the intensity of gravitational field is 0? Because at the center of the earth, the acceleration due to gravity is 0. Therefore, intensity of gravitational field is also 0. And also at infinity, the acceleration gravity is 0. Hence, the intensity of gravitational field is also 0 at infinity. So, this is the condition, right? At a point, it is, next is what is, this graph is very important. You will see this graph. Next is gravitational potential. Gravitational potential and potential energy of potential energy at a point, away from a body. That is what we have to see here. Gravitational potential and potential energy. Here also this is that there is a body of mass m, right? There is a point P where the potential or potential energy potential energy at this point has to be calculated, right? All these are the gravitational field of this body. For example, this point P is in the gravitational field of this body. The point A is also in the gravitational field of this body, and point B is also in the gravitational field of this body. We have to calculate gravitational potential and potential energy at a point away from a body, right? It is the work, the potential, potential what is, at first I am going to tell you what is potential, then we will come to potential energy. Potential at a point in the gravitational field due to a body. This is the body. We have to find potential at this point. Then what we have to do? You have to take a test mass of mass m from infinity to this point. What is the work done? So, potential at a point in the gravitational field due to a body is the work done in bringing unit mass from infinity to that particular point where you wish to find the gravitational potential or potential energy. Understand? For that, what you have to do? You have to take a unit mass from infinity to this particular point. Unit mass to get it is very difficult because we have to measure unit mass out of a body, so that is difficult. So, we will take a test mass from infinity to this point. This is what? Am I correct? So, we have to from the infinity to that particular point in the field. So, from infinity to the point P, when an object is brought, what is the work done by the system or anything, external agency? That is what is called the work done by the system or work done by the external agency. In this case is called gravitational potential, right? Now, suppose that there are 2 points in the gravitational field of this body. One point is A, other point is B, right? Between A and B, the distance is a very small distance. These two points are separated by a small distance dx. A is at a distance x from the center of the body, right? Therefore, if a mass m is placed, small m is placed at the point A, actually, we are going to take place what is the total amount of work done in bringing a unit mass from infinity to the point P only we are calculating. For that, we are taking 2 more points, extra points A and B separated by a small distance dx. And also now we will suppose that the mass, the test mass m is shifted from A to B through a small distance dx. What is the work done? Work done, everybody knows that is equal to force into displacement. In this case, suppose that the mass m is placed at the point A, then what is the force? Gravitational force only. What is the gravitational force? F is equal to G, m and small m. Suppose m is here only at the point A. So, a G capital M small m divided by x square. You have imagined that the mass m is placed at the point A, then the force of attraction between that small mass and the big mass is given by F is equal to G into capital M small m divided by x square. If the mass m is shifted to a small distance dx, the small attractive force, the work done by the attractive force, the small work done by the attractive force is given by dw. Suppose that this body attracts this body of mass m through a small distance ds. Who will do the work? the attractive force, gravitational force of attraction of the system will do the work. Am I correct? So it is attracted so that this body of mass m is shifted from A to B through what distance? Dx distance. What is the work done then? Work done is equal to force into displacement. What is force? G capital M small m divided by x square into dx. If the body is, so for a small distance in the field to be shifted, the small work done is this much. So, small value when obtained, the big value can be calculated by integrating the function, right? That is what we are getting. Small value of shift, the work done is this much. Therefore, if the body is shifted to infinity to this point, the total work done can be calculated. That is the potential energy at that point. Am I correct? If the body is moved, so hence if the body is moved from infinity to R, infinity to R means from the body to infinity to, from infinity to the body to infinity to the point P. Point P is R. That means from infinity to R. From the body to infinity, what is the distance? Infinite distance. Right? You are bringing the mass m from infinity to m. That means when the body is shifted from infinity to the point P, that means a distance up to a distance r, when the object is shifted, the total work done. For a small work done, this is the work done. Therefore, for the total work done in bringing the body from infinity to the distance r from the body, the work done is given by W is equal to integral infinity to R. First, the body was at infinity. Now the body is at P. At P means the body is now at the distance R. Hence, we can say that the work done in bringing the body from infinity to R, the total work done is given by integral infinity to R G capital M small m divided by x square. Actually, wrongly this negative sign came here. You have to change it. This negative sign is not there. You have to change that. G capital M small m divided by x square into dx. Am I correct? So please note this. Wrongly I wrote this negative sign, marked this negative sign. Negative sign is not here. You will not write this negative sign here. Okay. This is equal, all the constants are taken outside, G, capital M, small m, all these are taken outside, and integral infinity to R 1 by x square dx. 1 by x square is equal to x raised to minus 2 dx. Integral x raised to minus 2 dx is equal to G, capital M, small m into x raised to minus 2 plus 1 divided by minus 2 plus 1. That is equal to G, capital M, small m into x raised to minus 1 divided by minus 1. This minus is taken here, that is this minus. That is minus G capital M small m into x raised to minus 1. X raised to minus 1 is 1 by x. Limit is also applied here. What is that? Infinity to R. So, how the limit is applied? When limit is applied in such a way that upper limit first in place of x minus lower limit. That is minus G capital M into 1 by R minus of 1 by infinity. Everybody knows that any quantity divided by infinity is equal to 0. Therefore, this cancels out. You will get the potential energy actually we are getting. We are getting the potential energy is given by U is equal, because work done is equal to energy. Who does the work? The body is doing the work, because the body is attracting the small body with a force F, and that force is actually doing the work. Who is doing the work? The body is doing the work. And you are getting the value of work done. Work done is equal to energy. A stored energy is called potential energy. Therefore, U is equal to minus G capital M divided by R. This is the potential energy of the small body of mass M at the point P, which is at a distance R from the big body. From the big body of mass capital M, the point P is at R. Right? When a body of small m is placed at the point P, that will have some energy. That energy is equal to minus G capital M small m divided by R. This is the potential energy. Right? Negative sign shows that this work is done by the system. The system, the big body is actually doing expending its energy to attract the body and doing some work of its own. So it loses its energy. That is why this negative sign is appearing here. This work done is by the system. This work is done by the system. This work done is by the system to bring the body of mass m from infinity to distance r. Hence, the system suffers loss of energy. That is why the negative sign appears in the relation. That is why this negative sign is there. Am I correct? Now we can calculate potential at that point. Potential at that point means total work done per unit mass. Total work done is potential energy. That is potential energy at a point per unit mass. If unit mass is brought from infinity to that particular point, what is the amount of work done? That is what is called potential. That is potential, it is given by capital V is equal to U by M. U is the total work done on mass small m. Therefore, work done per unit mass means total work done divided by total mass, work done per unit mass. That is equal to minus G capital M small m divided by R divided by M. M and M cancelled is equal to minus G M by R. This is the potential at a point in the gravitational field due to a big mass of value capital M. Am I correct? So, potential at a point is independent of the mass of the small body, but it depends only on the big mass. When the mass of the body, big mass increases, then the potential also increases. And also potential at a point towards the big mass increases because potential V is inversely proportional to R. Am I correct? In the case of the earth, if the body is shifted from a point R1 to R2, R2 is greater than R1. Suppose this is the position on the surface of the earth, this is R1 and it is taken to another position R2 on the surface of the earth. Then change in potential energy is equal to, change in potential energy means when distance increases, potential energy increases because it is a negative quantity. Potential energy of a body or in the gravitational field is given by minus G capital M small m divided by R2 minus. Distance increases, value increases. Right? Distance increases, actually negative value decreases. Negative value decreases means the value, positive value increases. That is why that when distance increases, potential energy increases. Suppose a body is taken from a distance R1 from the surface of the earth to R2. R2 is greater than R1, then there is change in potential energy. At the higher height, the potential energy is more than that at the lower point. That is why we can write when a body is taken from R1 to R2, there is change in potential energy. Change in potential energy is given by delta PE is equal to potential energy at the highest point minus potential energy at the lowest point. Always there is a negative sign in potential energy. This is equal to G capital M small m divided by R1. Right, minus into minus, right, sorry, this is minus into minus is plus here, this is minus sign only, don't be confused, right, yeah, that is minus into minus plus, this positive quantity I am writing first, then negative quantity, minus G capital M small m divided by R2. What can be taken out? That is G capital M small m is taken outside divided by 1 by R1 minus 1 by R2. Right? This is the general expression for change in potential energy when a body is shifted from R1 to R2 from a big body of mass m. Right? A small body of mass m, small m is shifted from R1 to R2 from a big body of mass capital M. Then the potential energy is change in potential energy is given by G capital M small m into 1 by R1 minus 1 by R2. Right, okay, here we can assume one thing. Suppose that if R1 is equal to capital, in the case of the earth I am talking about. Suppose an object is placed on the surface of the earth, then R1 is equal to capital R, radius of the earth, okay? And now it is taken to a height h above the surface of the earth, then R2 is equal to R plus h. Am I correct? Then delta PE is equal to G capital M small m into, in place of R1 you will place 1 by R minus 1 by R plus H. Right? LCM is taken and crossing it, you will get R plus H minus R divided by R into R plus H. Right? Then R and R cancel, you will get G capital M small m into H divided by R into R plus H. Am I correct? H is a height from the surface of the earth. That height, when compared to the radius of the earth, it is very, very small. Therefore, H can be neglected. In that condition, in this experiment, H is neglected, then we will get what? Delta PE is equal to G capital M small m into H divided by R square. This is because H is R into R is equal to R square. That is equal to G capital M divided by R square into MH. But everybody knows this value. Everybody knows, I suppose everybody knows. G M by R square is equal to small g. Therefore, this is equal to mgh, because everybody knows that when an object is taken from the surface of the earth to a height h, the potential energy is equal to mgh. That also proved. This is the potential energy, right? This is the topic, today's topic about, right? Tomorrow we will come with another topic. Till then, bye bye. Thank you very much.